right, well, sorry. All right, welcome back, everyone. We're ready to start the next session of OARC 39. Please remember to participate in the poll that we post in the workshops channel, and also remember that you can post your questions there for the speaker at any time, and prepend them with hashtag questions. Our next speaker for today is Sandoche, and he's going to talk about the public key infrastructure for IoT using the DNS infrastructure.
Waiting for the presentation to go online. My name is Sandoche Balakrichenan, and I head the R&D partnerships at AFNIC. AFNIC is the .fr registry. Okay. Yeah. The title for my presentation is PKI Public Key Infrastructure for IoT using the DNS infrastructure. Okay. I knew the question was there, so I put the slide earlier, but I had the question today afternoon during lunch. So here we are not adding anything new into the DNS infrastructure or any new resource record. So it's just reusing what is there existing. So I will start with a use case, a real use case. The network is called LoRaWAN, Long Range Wide Area Network, and it is used for many applications. I think it's around using 30% of the applications are using LoRaWAN now, as per the market studies. So we take the use case of LoRaWAN for this presentation. So here, this is the architecture of LoRaWAN. LoRaWAN is a star topology where you have the end device. There you see the end device on the left, and there is a gateway. The communication between the end device and the gateway is done through a RF radio frequency technology called LoRa, long range. And from the radio gateway to the different servers, we have the network server, NS, application server, AS, and a joint server, JS, which is at the IP space. So it's common internet protocol that has been used. So to communicate between the end device and the different servers in the network IP space, LoRaWAN uses 128-bit AES symmetric keys. So the keys need to be shared earlier between the end device and the servers in the IP space. So there are issues currently where how the keys could be shared. So we say the pre-shared keys. So what happens is that the devices, when they are manufactured, the manufacturer adds the information into the device, like the keys, the ID, and etc. And that keys need to be shared with different stakeholders. The different stakeholders, I'm not going to tell all of the names, but as you could see, so all these stakeholders sometimes need to be taken this information. That could be one or two stakeholders, but there could be others also. So currently, how is it shared? If you could see, sometimes the keys are printed behind the device. They are sent via mails, or sometimes you can use NFC to see the pre-shared keys. So it is not really secure, as you could see. But there are some proposals, there are some applications where they have secure elements, etc., etc. But this technology, what we are talking is like for €1 in a year. So if we add more complications, then the cost of the technology increases and its real use case is not there. So that is where we were thinking that can we use what we are seeing in the normal internet, that is asymmetric keys, could be used that in this use case. So we divide them into two different sections. One, as we have seen in the architecture, the radio frequency space and the IP space. So we tried to solve the problem in the IP space. So in the IP space, where you could see we have interactions between the application server, the joint server. The joint server is the authentication and authorization server. The joint server and the network server, and the network server and the network server in case of roaming. So this is one a small screenshot that I have from the LoRaWAN backend specifications. So how the security should be done is left to the person who are implementing. They don't, it is not normative. So we could use HTTPS. So currently, if you use normal CA type certificates in the IP space, I'm talking about the IP space, not the radio frequency space, between the different servers in the internet, we could use normal CA certificates, but the CA certificates which we buy, it is expensive, and if you add that, it comes to more dollars per device. So one of the solutions could be using self-signed certificates. And the next thing is that when we use certificates like Let's Encrypt, they have restrictions for 8 labels. But here we have we have the identifier for the device where we could have dots between each numbers. So it comes to 16 label length, and we were not able to use certificates like Let's Encrypt. So the only solution was self-signed certificates. And then we have, for example, in the web communication, we have a CAA bundle, Trust Store, where the digital certificates are validated by the browsers. They have a list of certificate authorities in the Trust Store. This is not available in the IoT software stack. So one solution could be using DNS-based PKI. So how it is done? If you see, here I have an example. This is how the backend specifications of LoRaWAN is written. So they have a domain called LoRaWAN.net. Under the LoRaWAN.net, you have a join UI and a net ID. The join UI is used for communicating with the joint server, the identifier for the joint server, and the net ID is the identifier for roaming. So communication between one network and another network. So the identifiers are like this. For example, in the join you have 16 digits which are reversed and dots are added between each digit, and you add LoRaWAN.net to identify the joint server. And in case of net ID, you have only 8 digits. So this is how the provisioning is done. We did an experimental setup with an university. So I'm not going through the complete architecture, but here, for example, if you could see the device, when it starts bootstrapping, it sends a join request, and in the join request, you have a join UI and the other information. And the network server, what it sees is that it takes the join UI, and then it converts into a domain name, and it looks at the DNS to identify the joint server. So that's how it is done here. So I'm not going through the complete setup. So what we did was that we had 2 experimental setups, one with a university which is called Telecoms with Paris, and one at AFNIC Labs. So we had 2 setups, and we wanted to test roaming here. So what happens here is that if we have different root CA for Telecoms with Paris and AFNIC Labs, it will not be able to understand each other, because there is not a common authority to validate that. So what we did was that we had emulated as the root CA, and we created the intermediate CA for the Telecoms with Paris, and the intermediate certificates, Telecoms with Paris, could be used to produce the leaf certificates for the different servers. So this is an issue, as it is a single root CA, and it could not be used when it is scaled. So that's an issue. So this is where can we solve this using DNS-based PKI, that is DNSSEC and DANE. I'm not going to explain what DANE is, because all of you know that. So there is a working group called DANS in the IETF. DANS is DNS Authentication of Network Clients Everywhere. In that working group, there are 2 drafts which says that how we can use DANE client ID during TLS handshake. So there were already implementations for the 2 drafts. It was done by Shumon Hook, And we took these implementations and implemented it in our LoRaWAN use cases. So it was updated, the TLS library was also updated. And then we did the test using the using this DANE client indication with the university. And in this case, what happens is that even if the university itself has its own CA, we are able to validate it because you can look at the you can look at the TLS-RSS record and get the hash of the digital certificate and then validate it. So the single PKI issue is solved here. So that's why we say here, due to this DANE-based TLS resource record validation, we could have multiple root CAs and not a single root CA. So an ideal scenario, so as of now what we did was that we have tried to solve only the problem of the IP space. But an ideal scenario should be that we should be able to have end-to-end security using asymmetric keys, that is the public keys that current as used in the internet. So how it could happen is that we could have a lightweight key that is being added to the device during the commissioning of the device, and that is shared with the DNS provider. That could be a solution, but the issue is that a X509 digital certificate is normally around 2 kilobytes. And there are work that is done that it compresses maybe up to 100, 150 bytes. But in LoRaWAN, if you see in the US, the minimum payload could be 11 bytes, and in Europe it is like 53 bytes. So we need, when the communication to be done, should be around like in the range of 50 bytes. So that's not a, so the X509 digital certificate using directly in the LoRa radio frequency network is not possible as of now. So what has been solved here? So we are not able to solve the issues in the constrained IoT device in the network, that is the LoRa RF space. But using DNS-based PKI, we are able to solve the issue of not having the CA bundle in the different servers in the IP space. We are not adding any cost because we are using self-signed certificates and DNS. In the case of having a single PKI, we can now have a federated PKI, so the closed security infrastructures could even communicate with each other. Then it is scalable, and bootstrapping trust is possible because this information had to be added only in the DNS, so we don't have any prior sharing of the keys. So we have some code as well as tutorial in GitHub, and we are also looking at IETF, such as the LPWAN low power wide area network work group, where when we presented this during the IETF 113, they said we are not security experts, but security experts were saying to us that maybe you could fragment the keys, and that keys could be sent over. So we could use a protocol called SHIC, static context header compression, that is an RFC in the LPWAN working group. This is an ongoing study. And also in the IETF working group called LAKE, Lightweight Authentication Key Exchange, they have in the charter the use cases like LoRaWAN, where they want to use cores and other structures to compress the public keys. So it is still ongoing study. So that's it. And if you have any questions.
Thank you. Please post any questions you may have in the workshops channel or come up to the mic. My first question would be, in your DNS-based infrastructure, where does the validation actually happen? Does the IoT device has its own resolver, or do you trust an external resolver that the IoT device is talking to?
So, as I said, we have two different spaces. One is the radio frequency space, where the IoT device communicates with the gateway, and we have the IP space, where the gateway communicates with the different servers in the internet. So the IoT device doesn't have the capability to resolve and validate, and that's a problem that has not been solved. So where we are solving is that you have the different servers, the servers like, for example, the network server and the joint server, when it communicates, it should do mutual authentication. So for mutual authentication, you have a TLS communication being established, and during the TLS communication, you ask for the digital certificate as well as the DNS client indication. So when you get the digital certificate, you look at the DNS resolver to get the TLS resource record, and use this TLS resource record to validate that with the digital certificate.
Okay, thank you so much. Any further questions?
Thank you.
Thank you. So the next presentation is the intentionally broken DNS server by Marc van der Waal. Marc, I hope you're ready early. All right, the floor is yours.
Well, hello, I'm Marc van der Waal from AFNIC, the registry of .fr. I joined AFNIC about 6 or 7 months ago now as an R&D engineer. And today I'm going to talk about IBDNS, the intentionally broken DNS server, which is one of AFNIC's latest projects. So when I joined AFNIC, I started working on ZoneMaster. It's a collaborative project that we have in common with Internetstiftelsen, the registry of .se. And I started quickly wondering, how do you test a testing tool? Now, what we do have already are zones that contain resource records with invalid data, or badly configured zones, for example, with broken DNS keys or broken trust chains. But for some other things, this is not always enough. For example, here, I have an example of a test case that ZoneMaster uses. And one of the things it checks is whether responses to SOA or NS queries have the authoritative bit set in the header. Now, the problem is with off-the-shelf DNS servers, you don't usually have the possibility of messing with the header. So that's how IBDNS came to be. When I'm breaking DNS, one way to think about it is to see it in layers. And IBDNS is able to intervene on all of these. So for example, the most basic way of breaking DNS is, of course, not listening on TCP. Moving upwards, we can mess with compression pointers or flipping bits randomly. We can intervene on the header. We can also have incorrect implementation of case folding, as specified in RFC 1034 and 1035. And as of now, it's still a work in progress, and other things are planned, like doing eDNS or even DNSSEC later. The architecture of this server is therefore a bit different from usual toy DNS servers, because we need to both specify which zones to serve, but also how to break them. This is done by a configuration file that both points to zone files, which are loaded into one database, zone database, and also the same configuration file populates another database, which is independent from the zone database, in which some subtrees are given the order to, for example, have case-sensitive searches. or for some other subtree have random bit flips. These two databases are structured in a way that I can have one zone file, but have different configurations for particular subtrees inside the same zone file. So this gives me the granularity I need for example, breaking just one resource record, or just a subtree, or a whole zone, or the default processing even. These two databases means that when I'm handling a query, I have to perform two lookups. So here I have configured some behavior for bitflip.example.com, and I'm processing a query for hello.bitflip.example.com. And the first thing IBDNS does is search for the nearest ancestor of hello.bitflip.example.com, and it finds a configuration for that, and this influences the way the query is handled afterwards. Now, moving to some examples. So I'll first say that I have prepared these examples with the same set of zone files in the same configuration. I did not restart the server or anything between any of those examples. So here, for example, we can see in DNS we're supposed to have the same case between the questions and the answer sections, but here I've configured a few subtrees in where this is not the case. And IBDNS is capable of either forcing everything to uppercase in the answer section or to lowercase. And in the last example, I'm just returning the original resource record as it's typed in the zone file. The second example here is when I'm touching the header flags, and here I set up a zone AA0.badflags.test that forces the authoritative answer to 0. And as you can see here with dig, this is the case. And now when I run zone master on the subzone, you'll see that I get the warnings I was looking for. That I do not get an authoritative response on SOA and NS queries. So mission accomplished here. Now, let's move on to something a bit nastier. One of the things I implemented in IBDNS is random bit flipping. So in a way, it's kind of fuzz testing. So here I've configured a few resource records, and if I enable random bit flipping on these, you'll see how these can get corrupted. So here I've highlighted the differences in yellow. We can see here that the AAAA resource record got corrupted in unknown type, and so dig returns that with the usual unknown resource record format. The text gets corrupted, and dig gives also a warning that the message is malformed. Now, when you try this sort of thing out, it's hard to determine whether you're actually testing your server or actually testing dig, because, for example, in some other case, the corruption is so bad that dig just gives up and gives you the hex dump of what it received. Here, this is due to a bad conversion pointer highlighted in yellow again. C0 OC got corrupted into C8 OC, which is the owner name of that last text record I showed you previously. Then I was wondering what happens if I run zone master of this obviously very broken zone. Well, so I ran this command in the loop for about 10 minutes. This loop would only exit if something crashed, and sure enough, I eventually got a segmentation fault. As a matter of fact, this is not in denial of service of the website zonemaster.net because the tests there are run in a separate sub-process, but still, it's a bug that I wanted to fix. So I looked at the last resource record that ZoneMaster tried to decode before it crashed, and it was an A record that was corrupted into a CAA record. The type A is type code 1 and CAA is 257. And of course, the contents become nonsense. But it wasn't the parsing that was the root cause of the seg fault. What happens instead is ZoneMaster uses LDNS for DNS packet handling and decoding and especially converting back to text. And what happens was that we use the C function to turn wire format data into legible text without checking whether the function returned a non-null pointer to a string before using it. So, fortunately, a fairly trivial thing to fix, and this is how I contributed to ZoneMaster for the first time, by finding that subtle bug with my little toy server. So what can we take away from all this? So I'm hoping to fill a void in DNS testing software with this intentionally broken DNS server. And I know that this project can also be used to explore gray areas in some RFCs, especially the older ones. It can also be very useful to reproduce incorrect implementations of DNS that have been observed in the wild, and maybe also find bugs and even vulnerabilities maybe in DNS libraries. And if there's one lesson I learned, is that it's always useful to fuzz test your software even when you are relying on mature and battle-tested libraries, because whatever you build with that can be a source of bugs, and you can have some very surprising things. Thank you. Are there any questions?
Thank you so much. So if you have any questions, please post them in the workshops channel or come up to the mic. John.
Hi, John Todd with Quad9. So of course there's arguably only one way for DNS software to work correctly for particular types of queries, but there are an infinite number of ways that you can fail. How do you choose which failure modes to include in your software? I'm interested in where you get the catalog of all the different types of failures and how you organize them, because this seems to be an n-dimensional problem if you're going to try to capture every failure mode.
Well, for now, I've been mostly focusing on reading the RFCs and having a bit of a adversarial interpretation of these. That is, thinking about every requirement and how people might do things wrong. And I'm also looking at what are the most common issues that ZoneMaster sees for certain domains under test. I'm also very interested in what's being posted in the various Mattermost channels on DNS-OARC, because these are also incorrect implementations that can be reproduced if need be. So,
thank you.
You're welcome.
Ed Lewis from ICANN. For the fuzz testing, have you tried to make the fuzz testing be more predictable? In other words, you tell it where you want the breakage to be. Because my experience with random errors, and I've had a lot, you want to know where they're going to be in a testing tool, so you look for it there. So, I mean, this is great to do random bit flipping, but you might also want to have the ability to say, I want it to bit flip this one or that one, and so on. So you want to be in control of your testing environment, is what I'm saying. Is you want predictable and repeatable to find these errors. I mean, besides looking around all over the place is great, but you want to repeat it because you're going to need to repeat when you find something interesting.
Yes, that's true. Very good points. But this is something I'm planning for as a feature for the future, because I've noticed already that I got the most interesting results when the resource record type or even the resource record length fields are somehow corrupted. So I will definitely be adding a plugin later to corrupt this sort of thing more predictably.
Peter Van Dyke wants to know if he can download intentionally broken DNS anywhere.
Well, we are thinking about, we're still debating whether to release the software to the general public or maybe share it within a more closed circle, because I'm very aware that it can be pretty dangerous for someone to set up a server that's intentionally broken and maybe delegates a subtree of the DNS to it. So we want to treat very carefully before doing so.
Manu Brutel Meta, I guess a comment back on what you just said. I mean, people can shoot themselves in the foot, but there is value of the software, and I think it would be useful to use. Another thought is, have you thought of using it as a proxy in front of an authoritative server, let's say, and do the bit flipping or whatever or change on certain specific requests? And if you're a proxy, then you can also add packet drops, latency, and stuff like that. And this is more in the case of testing the behavior of the clients versus just testing the authoritative side.
Well, it could be indeed useful if IBDNS had a proxy feature. Since the software is in a very early stage, I'm still open for suggestions of possible features, and I'll take note of that.
I would like to know, my understanding currently is that intentionally broken DNS focuses on random bit flips and sort of a safety aspect of the parsing library. Do you have any plans to extend that to, let's say, more security relevant features such as signature verification?
Well, for now, I do intend for IBDNS to not just focus on random bit flips, but it's just it being a feature among others. My original design goal is still to explore what people get wrong in the DNS RFCs. But when it comes to signature verification, this server is only meant to be an authoritative-only server. So, to my understanding, this shouldn't do much of verification, unless I'm mistaken, of course.
And one more question from the workshops channel. Sorry, it keeps scrolling away. Where is it? I think common open source is already tested by OSS Fuzz project by Google. Can this discover entirely new kind of issues?
Can you repeat the final sentence?
Yes. Can this, I'm assuming this is referring to intentionally broken DNS. Can IBDNS discover entirely new kinds of issues?
Well, it's too early for me to know with certainty if I might uncover anything, but I'm hoping.
One more question. Are you aware that DNS lookups are case insensitive but case preserving on response?
Yes, I am.
Okay, great.
I wanted to say, by the way, I didn't show the default behavior of IBDNS with that regard, but it does preserve case by default.
Thank you so much.
You're welcome.
All right, the last talk of the session will be Observable KINDNS, Validating DNS Hygiene by Raffaele.
Good afternoon, everyone. I'm Raffaele Sommese. I'm a last year PhD student at University of Twente. And today I'm going to talk to you about this observable KINDNS, in particular about the measurability of the KINDNS practice. For those of you that doesn't know what KINDNS is, basically over the years, the way that we defined best practice for DNS ecosystem was defining RFC. So every time that we want to introduce a new best practice in the DNS ecosystem, what we do, we wrote an RFC, we published that RFC, and that slowly operators start to take over this RFC and start to implement this RFC. However, this mechanism was basically a mechanism where the operators need to decide which RFC they want to adopt and which RFC they don't want to adopt. But this decision impacted the security of billions of users on the internet. So at a certain point, ICANN, in collaboration with the operators, decided to do a different thing, decided basically to codify a set of global norms from this best practice and call this set of global norms KINDNS, knowledge sharing and instantiating norm for DNS and naming security. It's a really long name. So what this is coming from? This is basically it's coming from a similar concept that was born for router security that was called MARS. MARS, it's a project for increasing routing security, where basically operators voluntarily commit to a set of practices that improve the security of the system. And many operators have joined this project, so I can decide why not give a try with DNS and why not try to develop something similar for DNS. However, there is a challenge in both of these initiatives, and this is what I want to contribute today with this talk. It's basically the challenge is how we can measure effectively that operators decide to adopt this practice. So how we can effectively see if operators are adopting this best practice or not. And the way that we decide to do this is to try to see if these best practices are measured from external third parties by leveraging previous academic research and by leveraging publicly available datasets. So if we look to KINDNS best practice, what we will see is basically that KINDNS has a different kind of best practice, both for authoritative name server and recursive name server, and there are some best practices that are common both to authoritative and recursive. And the KINDNS best practice both address public-facing infrastructure, so infrastructure that is exposed over the internet, but also private infrastructure. For this talk, we'll just talk about public-facing infrastructure because addressing private infrastructure, obviously, it's a more challenging task. And we identify basically which are the practices that are measurable and suggest basically additional practices also that are not currently in KINDNS. And I want also your opinion about that if you think that this practice should be included. So let's first start from the authoritative best practice. So the best practice to operate authoritative name server. And I mean, you can find this best practice pretty obvious, but obviously this is something for all the kind of DNS operators that are out there. And the first best practice for sure is to enable DNSSEC on your authoritative name server, so provide DNSSEC signed answer. And the question is if this best practice is measurable. The answer is yes. This best practice is currently measurable and it's currently measured. And this can be measured at two levels. Can be measured at large scale with the active DNS scan. One of the examples that I put here, it's OpenIntel. It's a project that scans around 60% of DNS second-level domain namespace every day. So we can run this assessment for every day in the DNS for 60% of the domain. But you can also measure this kind of practice by yourself, by, for example, using tools like ZoneMaster, DNSViz, or HardenHides. The second practice that was defined in KINDNS is basically geographical, topologically, and name server diversity. And also this is a measurable best practice by using active DNS data, again, prefix to AS data, so data that converts IP address into ASN name and geolocation data, for example. And again, with ZoneMaster, DIG, and geolocation data, you can measure these things by yourself. Things get more tricky when we talk, for example, about the best practice in KINDNS that says that you should forbid zone transfer And you should avoid that people that has no access, you should protect your zone, your authoritative server from zone transfer from unauthorized source. And this is, I put maybe as measurable, because I'm sure that if tomorrow morning I will start to scan the entire internet looking for zone transfer available name server, people will get really upset about it. So how we solve this issue for doing like large scale measurement? And I mean, if you want to do with tool, sure, you can just do this with DIC. And last one, it's a sort of measurable best practice, but it's a measurable best practice that you need to do manually because they ask you to implement two-factor authentication on your customer portal for managing their DNS record. Now, look into the recursive part. What we have basically the same things of authoritative server as first practice, that is enable DNSSEC on your recursive name server. In this case, they talk about enabling DNSSEC validation. And sure, this is easily measurable. It's not currently measured by anyone, at least at my knowledge, at large scale. But this can be easily measurable by looking, for example, to the full list of OpenResolver scan and start to query these OpenResolvers for their support for DNSSEC. And the second one for recursive name server, it's QNAME minimization. So if recursive name server adopt or not QNAME minimization. And this is not fully measurable. This can be done, for example, with the day-in-the-life DNS traces from OARC. But it has a limited visibility towards how recursive name server implement this QNAME minimization. So we can have a partial picture for this kind of practice. Then we have a set of best practices that are common, both authoritative and recursive name server. The first one is that you should not put your authoritative name server on the same server where your recursive name server lies, basically not use the same server for recursive and authoritative. And this is surely measurable by using basically active DNS scan and OpenResolver scan. However, it has a limited coverage because, for example, you can run recursive name server just for a subset of your IP space, and then we have no visibility about that. Or you can run an authoritative name server on your recursive name server for a series, little set of names, and we don't have visibility about this. Then the second practice that you have is software diversity, and I know that this practice has caused a lot of discussion in KINDNS mailing lists because it basically says that you should use diverse DNS software to increase the resilience against bug, for example, of a specific version of a DNS software. And also for this one, the measurability is really, really limited because basically you need to fingerprint your DNS server. Again, if I start to do version.bind query, or if I start to do nmap towards IP address of authoritative name server, people will be really upset about that. And same things applies for ACL. There is these requirements of basically restricting access to third party to non-essential service on authoritative names and recursive name server. And this can be done, for example, with port scan, but it's still a problem of how to do that responsibly. And the final one is prevent spoofing and hijacking through implementing MARS and BCP38 best practices. And this can be actually easily done by just in the same way that we assessed MARS policy. So there are then some series of practices that are completely not measurable from KINDNS. These practices are basically the necessity of having a monitoring system, necessity of having internal ACL. There is a best practice on how to handle your SSH authentication for authoritative and recursive name server. And this obviously it's completely not measurable from a third party. And there are best practices on server hardening, integrity, and versioning. And there is one best practice actually that is not effectively measurable from third party at current state, that is zone integrity. Basically, it says that you should keep your zone as, the integrity of your zone as much as possible. And the way to basically assess this is to check if there are NS hijacking, for example, in the zone. But this will require things like rapid zone update instead of sharing, for example, zone with the third party once a day through ZDS program. And finally, I have a sort of missing best practice that are not mentioned in this KINDNS program, but I think, I mean, and as a researcher, important. One, there is no mention about Anycast. And especially for critical zone, we have seen that Anycast is really important for outcoming DDoS attacks. So maybe it's worth it to be considered. Also, there is no mention about caching best practices. And for example, think about using long TTL value for your DNS infrastructure record, for your name server record to increase the resilience against DDoS attack. And the last one for practice that is missing, I think it's check the consistency between parent and child zone in your DNS authoritative name server. This will prevent, for example, inconsistent delegation or lame delegation. So these best operational practice at the end represent a fundamental pillar in improve the DNS ecosystem resilience and security. And what I can and we can do as an academic researcher, it's if there is interest in third-party independent validation of these best practices, we should seriously consider which of these practices are measurable and which of these practices make sense to include in the KINDNS best practice in the view of the measurability of the practice. So the main goal here was to understand the measurability of this proposed practice and other possible practices. So to conclude, basically, assessing this best practice requires a strong collaboration among different stakeholders. There are academics, there are independent researchers, there is ICANN, there are operators like you, that if we work in synergy, if we share data, if we share knowledge, and we can improve the DNS security ecosystem. For example, on this sharing data, on OpenIntel we measure 60% of the DNS ecosystem every day, but we are mostly measuring GTLDs. We have limited visibilities on CCTLDs, and this is because obtaining zone from CCTLDs, it's difficult because of legal agreement that needs to take place. So one thing that could be useful is to have more data from CCTLDs and be able to measure also CCTLDs domains. And yeah, basically this data and knowledge sharing represent one of the key to achieve this goal, basically, for a better measurability of this practice. And the good thing is, at the end, is that some of these practices are already measurable today. Some of these practices are effectively already measured today. We have already done some studies on this practice. So we can see if after this implementation of these norms by part of ICANN, if after operator joining this project, if there will be like an improvement in the overall DNS ecosystem. So I want to leave you with some question that maybe you can ask me back. And it's how a researcher can help to assess the conformance with these DNS best practices. What do you think it's missing in these KINDNS best practices? And what's the way to overcome this concern of data sharing that we heard over the years among community and operators to basically solve this problem? And with this, I finish, and I thank you for your attention.
Thank you so much. Please go ahead.
Hi, Lars Lehmann from NetNode. I think the first attempt that I saw to create best practice for DNS was back in 1993. Several attempts have been done since then. They have all failed. Because it's not a single system that you can create a black and white checkered thing for, because it has dynamics and it has different interpretation and it has different approach to various types of things. For instance, if you have a vast autonomous system that stretches over 3 continents, and inside you have 15 nodes operating in an Anycast internal cloud from 2 different IP addresses in the same /24, it will fail. Whereas the 2 servers in the same city, in different autonomous systems, in different /24s, in the same ISP, will pass.
Exactly.
I will argue that that's not good. And also, when you create systems like this, where you end up with a green light or a red light, you shape the entire community into one stream, and that's actually a single point of failure. If you tell everyone you must use this type of SSH access, then the perpetrators will know that, that's what I'm going to attack. And you need to leave the field open for having variation. That diversity is very much the fundament of the DNS business. We must be able to use different approaches, and the customers must be able to choose. So what I would like to see is an explanation to say, here are the various choices that you can make when you're a DNS provider, and each choice will have the following consequences. And that will encourage people who buy this or people who work with this to learn more and to understand what the various effects are of different choices. And that's what we need to do. Not to give them a black and white thing that pull the lever and see what happens. Oh, it's red, that's good. Or the green, that's good. No, we need to educate. We need to teach people how to interpret the differences, and we need to tell them that the diversity is the very fundamental part of the DNS system. Thanks.
Yeah, I agree basically with what you said, and the things that to say this is effective, this is not effective, these are the different consequences that you can have from these choices. You need to be able to assess that, so you need to be able to measure that. So this is the fundamental part that I'm trying to drive. We need to share insight, we need to share information to be able to define better practices. That's the only way that we have. Otherwise, it's pointless to create a new RFC of the RFC, basically.
There's a comment in the workshops channel, a comment from a DNS software developer. To me, concerns about breaking something by doing scans on the live internet are hard to understand. There's so much nonsense and malicious traffic in the current real traffic that any scanning you can possibly add will appear as noise.
That's true, but in the moment that you do this from a responsible network, what you will have is lots of people angry and abuse email, and you need to stop because you cannot do that like malicious people do.
Rolf?
Yeah. I'll agree with Peter there. The problem with real data sharing is that there are all these legal implications, and with sort of the IP address, for instance, being a PII, that makes it difficult. But the actual thing I want to comment on, you said that you could measure resolvers. And I think the way how you want to measure them is simply impossible, because of a lot of the stuff that resolvers are sort of behind. Not every resolver is open. I mean, measuring open resolver gives you a certain data set, but it doesn't give you the world of the overall resolvers, because there are resolvers in ISPs, in enterprises, that you never get with these. So I would discuss that this is not measurable.
Yeah, I agree with you. At the initial stage, I stated that basically we are just looking to public-facing infrastructure, so something that is really exposed to everyone on the internet. But there are some aspects, and actually, in the practice of ICANN of KINDNS talk about like semi-public DNS resolver for some of the practice. So there is always something in that direction. But still, it's difficult to measure. You need to have internal.
The iceberg. I mean, the tip is getting larger, but it's.
Yeah, you need to have internal vantage point to do that kind of measure. I agree with you.
Yeah. Hi, Ray Bellis, ISC, and this. I think maybe touching a little bit on what Lehman was just saying, I'd actually like to challenge this sort of perceived wisdom that you shouldn't mix authoritative and recursive on the same server, because there are circumstances in which it's actually, I believe, a good idea. If you have internal recursive servers, they're not open ones, they're not public, they're serving yourself internally, and you've also got authoritative servers, then it's, I think, perfectly fine to have your internal recursors act as hidden secondaries of your authoritative zones. And it has the benefit that when your network, or if your network becomes partitioned, your recursive servers still have your zone data. They can still answer on behalf of your own zones. I think, perhaps I think when Meta had a problem last year, when I think just their authoritative servers actually got partitioned, that might have got them out of the woods at that point, because their recursive servers would still have known the data. On our own network, we're actually not using straight secondaries to achieve this, but I'm using Bind's mirror zone feature. And the reason we're doing that is that that allows these secondaries to also perform DNSSEC validation on this data that would otherwise just be served as authoritative data.
Yeah, that's true. I think the main reason for that not having recursive and authoritative on the same server was to basically to avoid the situation where, I mean, it's more easy to overload the recursive name server in terms of query, in terms of attacks. So if you want to protect an authoritative name server, putting a recursive name server on top of that, expose it to the internet, it's dangerous because you run the risk that someone...
But it's so often just stated as a blanket, you do not mix these. And actually, I think that's wrong. Yeah, I think there are sometimes perfectly sound engineering reasons why you should mix them. And I think it's a disservice to just perpetuate the myth that mixing recursive and authoritative is a bad thing.
Yeah, I agree with you. I mean, again, it's not like it's everything green or everything red. There should be something in the middle to define. It's like just a set of practice.
Okay. Thank you. Thank you again. Everyone, we're going to take a 9-minute break, and then we continue with the last talk of today. If you're attending online, please be aware that there's an online social event that will happen at 5:10 p.m. local time.
Testing, testing, testing sound. Hello, hello. Just testing the sound on my end in preparation for my upcoming talk. This is Deccio. Testing sound. Waiting for feedback from those that are in charge. Okay, sounds good.
All right, everyone, please get ready to continue.
Yeah, and about the online stuff, the online social business special channel, people access emails for their Zoom account.
Okay. All right, everyone, we're ready to start. Welcome to the last part of this first day of OARC 39. The last talk is going to be delivered remotely by Deccio. For this talk, even if you're attending in person, please ask your questions via the workshops channel. We do not have a microphone line for this talk. Also, may I remind you for the social event that happens online at 5:10 local time, you do have credentials for that received along with your Zoom credentials. Okay. Welcome, Deccio. And his talk is 14 years in the life, a root server's perspective on DNS resolver security. The floor is yours.
All right, thanks so much. It's great seeing everybody remotely. I'm so sorry I can't be there in person. I was planning to travel, by the way, because I have to be in Nice next week. But it turned out that it just became too complicated. And because my kids have an event that I need to be at tomorrow, that just sealed the deal. So sorry to be remote, but I'm glad to be participating nonetheless. So the title of my talk is 14 Years in the Life, a root server's perspective on DNS resolver security. And actually it's sort of a play on words because we're using a root data. So you could also say a root server's perspective on DNS resolver security. We'll talk a little bit more about what that means here as we go along. But first I wanted to start with some of the impetus for this. This came from prior research. In 2019, we did an analysis of source port randomization of DNS resolvers. We were using a method where we could reach resolvers with a given query. And then basically we could issue 10 queries to that resolver, which would result in 10 unique resolver to authoritative queries. And using that, we were able to recognize and determine whether or not source port randomization was being used. And in that prior research, we found that in 6% of autonomous systems, at least one resolver was lacking source port randomization. We found that to be somewhat significant, but what we really wanted to do was to analyze this at scale. How could we expand our analysis? So on the left-hand side here, we look at the research questions. What does source port randomization look like with a larger data set? We had found a method where we could just, using passive data, determine if a resolver was using source port randomization. And so why not apply it to a larger data set and a passive data set as well? And then while we were doing that, you'll see that we ended up using diddle data, we decided, well, what else could we use? Could we sort of infer from the data from this large passive data set in terms of other privacy and security mechanisms could be that we could observe. And then we also wanted to not just take a snapshot look, but see what things looked like over a 14-year period. And we, by the way, picked the 14-year period because we went back to 2008, the year of the disclosure of the source port randomization vulnerability that was publicized by Dan Kaminsky. And so the data set we selected to do this was, again, this is A-root data from the diddle collection going from 2008 to 2021. Now, by the way, there, of course, is other data in the diddle, not just A-root, but for various reasons, we chose just A-root to do. And one of the primary reasons was because not all root servers have data each year in diddle, and we wanted something consistent along the way. But we also had some computing constraints, computing resource constraints on the machines on which we did the analysis. But nonetheless, we have, it provides us a view into the DNS ecosystem at the things that we'll be talking about today. Now, what we did was, even with the data we did have, we couldn't look at things, take a complete view of things. When I say a complete view, for all the client IP addresses we were seeing, we couldn't look at like all the queries they were doing. So we collected a sample. And for the sample we were looking at, they had to be a sequential set of queries for various reasons. So we looked at most 13. The reason 13 was chosen was in case we had some repeat queries along the way, so we could throw out some of them. We needed unique queries. So that was the reason for that. We collected things like query name, query type, transaction ID, source port. And then we also collected the total, even outside of those samples, the total per query, per type query counts for various types, not every type, of course, but for many types. Okay, so the first thing we wanted to look at that goes back to our previous research was source port randomization. And so looking at over time from 2008 to 2021, that was the diddle data that was available to us at the time we ran this. Oops. Oh, here we go. So sorry, let me go back. So what we did was we identified 3 different categories. One was no source port variation. So they were using the same port for any query they were giving. Okay, this was sort of the traditional model, but we had 2 other categories. One of them was what we called a small source port pool. So like one of the earlier versions, I can't remember which version is, maybe, I can't remember. Anyway, one of the earlier versions of Bind would start up with like 8 source ports corresponding to 8 sockets, and then they'd use one of those. And so we could actually see from our analysis if we were using small source port pool as well. And then the last one was sequential port allocation, where you just get these sort of more or less, I mean, it was actually more sort of pseudo source port allocation, or pseudo sequential, I would say. And we did that by looking at if the source ports being used had a range of 100. So what we found was in 2008, and this was taken prior to the disclosure of the source port, lack of source port randomization vulnerability, that there are about half of resolvers that lacked source port randomization. And that accounted for about 75% of queries over on the right-hand side. Okay, so it took, though, even after all the publicity and everything, it took about 3 years. I don't have my arrow. There's my arrow. After 3 years, did the fraction of vulnerable resolvers halve in size? And that was sort of significant to us. But even in 2021, we see that about 4% of resolvers. Now, by the way, we use the word resolver somewhat loosely. We mean those within our data set that, for which the sample has these characteristics. So we're working on another project, incidentally, where we can do a little bit better identifying of what root data looks like, but I'm just letting you know what, sorry, I'm keeping track of time on this side as well. So anyway, what things look like now based on what we have. And by the way, the countries with the highest fractions of vulnerable resolvers China at 8%, India with 8%, and Russia with 5%. This was in 2021. Okay, there we go. Okay, we also looked at transaction ID randomization. This one is sort of a little less interesting. The smaller rates of vulnerable resolvers in that regard. We're using the same categories as we did with source per randomization. In 2021, we identified about 2% of resolvers that lacked transaction ID randomization. And there was one of the weirdest things we found in this was a high fraction of small transaction ID pool in 2009 and 2010. We found that 91% of resolvers in this particular category in that time frame made at least 2 queries for type MX with transaction ID 10. We're not sure exactly what that meant. We did our best to sort of look it up, but it was just a little bit of extra data to help us sort of identify what was going on. And in the end, we couldn't figure it out, but it was bizarre. And then it sort of declined after 2009, 2010, this particular behavior. We thought maybe it was an error in some DNS resolver software. Maybe one of you knows something about that and you can tell me about it. Okay. See, moving along. My slides aren't advancing very well. Oh, there we are. Okay. All right, back to, so at DNSSEC validation. Now, of course, with passive data, there's only so much we can infer with DNSSEC validation. And so we're looking at a heuristic here. And in this case, we were just measuring resolvers with at least one DS or DNS key query. And yes, I know that doesn't mean validation. It also doesn't mean not validation, but it's a heuristic. Okay, so we saw the first significant presence of of validating resolvers using this heuristic in 2013. Okay, right around there. So this is 3 years after signing the root. In 2021, we see 17% of resolvers making 70% of the queries exhibiting this type of validating behavior. According to our data, France has the highest fraction of validating resolver. It's 36%, followed by Russia at 29% and Brazil at 26%. Okay, so that's just some of the data that we found with regard to DNSSEC validation. 0x20 has been talked about for years, but we've not seen a comprehensive analysis of 0x20 encoding. It especially not trends over the years. And we wanted to see sort of where it landed. There was some discussion just now about, case preservation in queries and responses, which of course goes back to how 0x20 encoding can be used. Let's see, so the way we did this was, there's a little bit more to it in this, and there's a paper version of our presentation, but sort of in summary, we measured the resolvers with sort of a 50% chance of the characters in the labels being uppercase versus lowercase. Okay, like I said, it was a little bit more nuanced than that, because when you're dealing with a lot of different scenarios, you have to take those into consideration. Uppercase first labels for Windows names, for example, and all sorts of things. So anyway, there's a little bit more to it than that, but that's sort of the gist of it. In 2021, we found about 0.4% of resolvers is all contributing to about 2% of queries. This purple, this purple line that you see, that's sort of that's the number of autonomous systems with at least one resolver exhibiting 0x20. So that's a little bit higher. That's closer to 5% or so. But in terms of resolvers that we witnessed this behavior, it was only around 0.4%. So somewhat low. Looking at DNS cookie usage, and we measured this by looking at queries. And in particular, a resolver was labeled as supporting DNS cookies if it issued at least one query that contained a DNS cookie. So in 2021, we saw about 8% of resolvers making that contributed to 8% of queries supporting DNS cookies. Oops, sorry. And let's see. And that, but actually, that in terms of autonomous systems that have at least one resolver exhibiting support for DNS cookies, that's about 40%, which is quite interesting. It's the difference there. So, okay. So now one last one, QNAME minimization. So we measured this by taking the entire sample, again, this small sample of 5 to 13 non-root queries, because of course we needed at least one label to analyze this. And if we looked at for which the entire query sample consisted of one label, then we labeled that as QName, a QName minimizing resolver. Now, this is somewhat different than some of the previous studies that have looked at this. But we had, anyway, this is the way we ended up doing this as a heuristic. And we know it's not perfect. It's going to catch some false positives, some false negatives. But we wanted to not sort of exaggerate the results. And that's why we took sort of a conservative approach to what we were doing here. Let's see, at least in 2019 was when we saw our first sort of reasonable jump here with the addition of QName minimization to bind. That's that marker D that's in the slide there. And you can see other milestones along the way in this and in previous graphs. Internet draft on QName minimization, unbound resolver introduces QName minimization, et cetera. So just to show a few examples that are here. So it has climbed, and in the end, what are we at? About 10% or so of resolvers that show it. I think it's about 12 to 14%, I think is what's here, contributing to about 30% of queries, okay, based on our heuristic here. Okay, so what we wanted to do now is, in this slide, is show sort of a breakdown of capabilities based on release notes from 3 different open source resolver implementations, bind, not, and unbound, in order to do sort of an unveiling of some of the primary holistic characteristics that we saw of resolvers out there. And so as we go down the line, I did this so that we can do sort of a, one at a time. So this was the highest. 59% of the IP addresses that we saw querying a root, and this is in 2021, okay, had transaction ID, randomization, yep, source port randomization, sure, but they lacked the characteristics of DNS-OARC validation, 0x20 cookies, and QName minimization. So, okay, that's fine. Then we came down to the next highest was 13%. Where we saw the addition of DNS-OARC validation, okay, and that contributed to about 55% of queries. You can see there's sort of a breakdown of everything, and obviously I can't go through everything here, but again, this is 13% of querying IP addresses contributing to about 55% of queries, so this one's over half. The previous one was only about 20% of queries. Then we go in and we take away DNS-OARC validation and add support for DNS cookies, and we get about 8.5%. By the way, if what I haven't done is referred back to this list of support up at the top, meaning like try and mapping these characteristics to the implementations. So far, none of these actually map to what we'd expect for the implementations above. In other words, we're not seeing sort of the fingerprints of resolvers that we might expect to see. Until we get to this one. This one might match unbound if we look at the fact that the default is as of 1.7.2 to use QName minimization, and that 0x20 is not on by default, and DNS-OARC, depending on how you configure it, may or may not be on by default. That one could be. This represents about 5% of queries and 5.1% of querying IP addresses and about 3% of queries. So I'm gonna just go through the rest of these and show you what everything else looks like. But it's sort of just it gets worse actually as you go down. We're seeing this is sort of the low ones at the very bottom where you have 3% or so that only have transaction ID support and they're lacking source port randomization and so forth. So there are some bleak things at the bottom in terms of some of the client IP addresses that we saw querying a root in 2021. All right, here's a bonus slide that we have, and this just shows we measured DLB queries observed at the root to see what this looked like. You can see on the timeline here, this is the root zone signing in 2010, the sunsetting of ISC's DLV service in 2015. decommissioning of the DLV service in 2017, I guess. And then the official marking of DLV as historic. And so you did see as many as, let's see, autonomous systems with at least one resolver using DLV peaked at about 5%, even though we never saw DLV usage reaching 1% of resolvers. But of course, the numbers have been declining. So it's sort of interesting to look at just to see from the from the perspective of root, what DLV queries look like. Okay, we're still seeing about 1,000 autonomous systems as of 2021, about 2% of autonomous systems querying for DLV, which is sort of interesting. And then the second bonus slide here is just looking at IPv6 at a root. And you can see that in terms of IP addresses on the far left, meaning client IP addresses querying the root, they're still really, really small, even though there's been some progress since 2010 or so. In terms of autonomous systems with at least one IP address querying, you see a little bit more of a presence there, but it still is pales in comparison to the IPv4 client IP addresses. Okay, record types, what's actually being queried, you see a little bit more of quad A versus A at the root server. Query channel is sort of in similar circumstances where you've seen some improvement. That's whether the query came over the quantity of queries over IPv4 versus IPv6, and that's still pretty small. So just to summarize here, fixing bad security is slow. In 2021, DNS-SEC validating resolvers are relatively few, but produce the majority of traffic to A-root, is about 70%. And then removing old things takes time. So that is my presentation. I'm happy to take some questions. And I think the questions are all in the chat, if I'm not mistaken. But I'm gonna have to go back and find them. Sorry. Okay. Sorry, give me just a second to orient myself to answer the questions. Might be John. Okay, John, in your graph that shows QNAME minimization rates, query volume drops sharply at the right-hand side of your graph. Any ideas what that is about? Let me go back to that slide really quick. So, sorry about that. That is a good question. We suspect, actually, we talk a little bit about this in the paper. I think part of this was actually, we had a weird, there was actually just there was a decrease in data, or sorry, there was an increase in data in 2019 that was sort of bizarre, and we're not sure why that was. And so I'd have to go back and look at that. But the short answer is we're not actually sure about some of these. We looked into it. There's definitely a play between QNAME minimization and the results for DNS-SEC validation. And that's in part because you would expect to be seeing, let's see, I'm trying to remember how we put this. I may have to answer this offline because there's some nuances in the paper that I need to go back and remember, but we did some comparison there. Because of the queries you'd still need to see at the root regarding QNAME minimization that affected things. But in short, the answer is we're not really sure. We did some discussion about it in the paper, and I have to go back and double check on that. But it's a great question. So sorry, it's not a perfect answer, but I'll need to get the paper in front of me. Let's see. I'm looking for things with the question tag. I'm not seeing anything else unless someone wants to bring one to my attention that I'm missing. Okay, well, that might be it then. Happy to take any further discussion offline.
Okay, Casey, thank you so much.
Thank you.
This concludes the talks for today. Now, please remember to participate in the poll before they close at the end of the session in 5 minutes. For the online social event, I think it's starting right now, and you have the credentials received along with the credentials for your Zoom meeting. If you do not find the credentials in your email, please look at the workshops channel. It has detailed instructions on where to find the credentials. OARC PC member Hazel Smith will be there, and OARC staff Matt, Rebecca, and Steve also will be there. So go talk to them. For the local social event, the bus will leave from this hotel at the main entrance, and boarding will start at 6:20, and we will leave at 6:30. There will also be a return bus that is leaving at 10 p.m., and that bus will also stop at the Metropole Palace and then return here. When you leave, please remember to grab some of the COVID tests and masks if you need any, and if possible, please test yourself before attending the sessions tomorrow. Also, thanks to our sponsors, the workshop host, ARNITS and SOX, and also Center as the joint program partner for OARC 39, and lastly, VeriSign as the 2022 workshops patron. Thank you all for coming. I hope you enjoyed the time here. We had great discussions, and looking forward to see you tonight and tomorrow again.